All right, let's go back and talk about recurrence interval again. Remember that the idea is that we're talking about the average time, or you could do this in terms of space, for an event to return. And in civil engineering, that would typically be things like a 100-year storm, or maybe even more rare, a 500-year wind speed, and even more rare than that, 1,000-year, maybe associated with a ground motion. We can define these kinds of things for any of these natural hazards. These are just some of the typical kinds of return periods that we might be looking for. Right now, the usage here in civil engineering is that we're looking at designing for rare events. And that's because in civil infrastructure, usually the public's safety is involved, and particularly their life safety is involved. And so we want that probability to be very low. And we characterize these in terms of the chance of this happening in any one given year, or an annualized probability. So what we are really doing here when we say an average time for an event to return like the 100 years, we're actually more precisely defining what's the chance in 1 year that that event will happen. So 1 over this, whatever this number is up here. So 100 year would mean a 1% chance that a storm of a certain magnitude would happen in that 1 year. And this is a maximum kind of thing, right? You have various storms throughout the year, you record those, and then what's the largest one of those? That's the one that we're talking about in that particular year, right? If it's a 500-year wind speed, maybe that's 150 miles an hour. So that's the X sub n that maybe goes with that 500-year event in a particular location. And so that has a chance of a 1 over 500, which would be a 0.2% chance of a wind speed of that value or larger happening in that 1 year, right? So if you think about the big picture here, the larger the return period, then the more rare it's going to be, and also typically the greater the magnitude you're going to have experience. Right? So the probability background of all that, and why this works, and why we call it the average return period, that kind of thing, or the recurrence interval, and it's an average time, not the exact time, is that we're looking at first, these magnitudes are the maximums that are happening in any 1 year from 1 year to the next. And those maximums are assumed to be independent, right? So that means that we're not thinking about a global, as in big picture, consistent change in what's happening with the, say, the storms and that sort of thing. So that a little bit rules out the way we might be thinking about how climate change works. It does and it doesn't. It's a little bit more complex than that. But in the end, we're looking at whatever happens in 1 year is probabilistically independent of another. That may not be a great assumption, but it is the base assumption, right? We're also looking at what we call stationary, that the probability of this event is stationary or constant each year, right? So that we don't have that kind of variation going on. Again, in the climate change view of the world, maybe that isn't such a great assumption. Well, but from year to year, that probably doesn't change that much. It's only after lots of years that maybe this probability has a fairly large change. So in both cases, these are actually not that bad of a set of assumptions. We're also going to assume that we have Bernoulli trials. That means that we only have one event in each year, or we have no events. And that's really associated with this sort of maximum kind of idea that we're playing around with, right? So let's let X be then the number of events that are happening in Y years. And they're coming at us at Bernoulli trials with a constant rate from year to year, right? And there's independence from year to year. And when that's happening, we really have the binomial model that works here, right? So it's almost like a coin flip, except for it's not 50-50. It's, if it's a 100 year, it's a 1 versus 99 chance. So you could even think about that as a 100-sided die. In that case, numbers 1 through 100 are printed on there, and the only thing that matters is if the number 1 comes up, right? And so with the binomial distribution, the average then for a number of events for a binomial random variable is that mu is equal to n, the number of years we're looking at, times the probability each year. And in our case, for y years, that would be y times p. The variance of that is np times 1 minus b. Right? Now, another way to also look at this kind of situation is the time between the events, or maybe even the time until the first event. And with the same kinds of setup that we have here, that leads to the exponential distribution. Right? Now, this first one was, well, how many events do we have in y years? This one's just saying, what's the model for how long it takes to see the first event? And that exponential model is lambda e to the minus lambda t. There's your exponential function, hence the name of it. And lambda is the single parameter of the distribution. It's the rate parameter, right? So directly tied to these things that are coming up here. How many do we have per year on average type of thing? And the average of that time until the first event is 1 over lambda. And then the standard deviation is also 1 over lambda, which means the coefficient of variation here is 100%. There's a lot of variation is what that means. So if lambda is the rate parameter and we're talking about a 100-year event, right, then we might think that the time to return would be related. Oh, how's that all work? And well, that's an interesting question here, but it all is directly tied together. So let's even go back to this, right? If we have a 100-year event, we're looking at how many events we have on average maybe in 100 years. Then if they come along 1 per 100 and we have 0.01 chance per year kind of thing, well, we have 100 trials and they come along probability wise 1 over 100, then, oh, well, that's going to be an average of 1 event per 100 years, right? So let me go, I kind of said that in a really weird, awkward kind of way. So let me go back. If we're looking at the 100-year event, that means the chance in any 1 year, little p, the chance of pulling the ball out of the magic 1-year sample is 1 over 100, right? So then we've got 100 trials of those. So 100 times 1 over 100, hey, that's your total number of events of 1. And when we get down to then the exponential model here, then our rate parameter is essentially that 1 over 100, and 1 over 100 is 100, right? So that would mean that the average time until the first event is 100 years. That's the tie together of all of the stuff that starts up at the top of why we call it a recurrence interval of an average time. We're really looking at an exponential distribution and these rate parameters, but that all comes along with this notion of the 1 over n probability and chance in any 1 year, and then these Bernoulli trials and the stationarity and this independence that is happening here.